was due this morning, and you will get those grades back before recitation next week. And going forward, we're going to be moving away from differential or derivative calculus and moving more into antiderivative calculus. So thus far, if the way that I've been breaking the course material up for digestion is we did our assessment of limits, and then we've been working on derivative calculus. Now we'll be working on antiderivative calculus. So working in the opposite direction. I'll get my screencast going and we'll see what that looks like. All right. So the examples that we'll be going over today will primarily be from section 4.3. And to start, we'll talk about what an antiderivative is. So in order to do that, we're going to have to talk about the Fundamental Theorem of Calculus. And when I was learning calculus in high school, the Fundamental Theorem of Calculus was taught to us within the first week. And it was something that we were told to repeat back because the relationship, as the name would suggest, is fundamental in understanding what it means to go back and forth between a derivative and an antiderivative. One thing that I will note after having graded exam 3 is that there are a handful of students, actually more than a handful of students, who are struggling with what graph, so which, if we're talking about the original function, the first derivative, the second derivative, I'm thinking specifically about the graphing problems from the first section of the exam. And I would recommend that if you are struggling with, say, what information you can get from the graph of the first derivative versus the second versus the original function, that you go seek out extra resources on that, or come to me during office hours and sort that out, because that's going to be something that's really important going forward with antiderivatives. So circling back to the Fundamental Theorem of Calculus, this is the definitive theorem. This is loosely what you'll find if you Google it. And what it is if f of x is continuous on a to b, close bracket, and big F of x is the indefinite integral of f of x on a to b, close bracket, then the integral from a to b of f of x dx is equal to big F of b minus big F of a. So we should be able to recognize this as the change in f. So this function here, the integral of the derivative, this little f of x is a derivative in this case, and I'll harp on this a bit more, is equal to the change in the original function, where big F is the original function. And we can write this in a lot of different ways. And that's what I've got written down below here, is a couple different ways to think about this. So when you're asked to evaluate the integral of a function f of x, what function, when differentiated, gives f of x, that's what's being asked of you. So if you're so we can assume that this is a derivative, whatever this is, so you can treat derivatives as though they're an original function. So when I say derivative and I say original function, I mean if you take one antiderivative, so you're not taking two antiderivatives in the same way that we are able to take two derivatives. So say we're treating, got an example for this, say we're treating velocity as our original function. So typically we would consider x of t or s of t, the position function, to be our original function, but it just depends on what phase you're in. So if we know that the derivative of velocity is equal to a of t, we can extrapolate from that relationship to understand better what an integral is. So the integral of a of t, the integral function of a of t dt, is equal to the velocity of that function. A big difference between the definitive theorem and these examples I've just thrown up is the integral in the definitive theorem includes bounds, and it's not a mistake that there are closed brackets a to b when we're talking about this theorem, but that doesn't mean that we can't still evaluate integrals without our bounds, and we'll talk about that in a second. But one thing I will note before getting into that is that it's very important that when you write if you're writing an integral symbol, if you draw this little squiggle, you must have d something, dx, dt, whatever variable the derivative or antiderivative is being taken with respect to, you've got to have this dt. And we'll do examples when we get into graphing, and I would expect that would be next week. But again, this is all contingent on what Dr. Zielicki asks me to present to you. But at some point in the next couple of weeks, we will explain to you a little bit more in depth what this dt is, but basically it's a width. So if you think about your Riemann sums, it's like breaking it up in that sense. So moving into this next bit that I've got here for you, the area underneath the derivative of a function on a given interval is equal to the change in the function on a given interval. So all of these things, these are all just different ways of saying the same thing, with the exception of the fact that I've put And I've got some examples that don't have bounded integrals. But if we ignore that for the time being, all three of these things are saying the same thing. They're all different ways of interpreting the fundamental theorem of calculus. This is just the textbook definition, and we'll apply. It's useful to have this sort of this English version I refer to. So more of a conversational version of what the fundamental theorem is, rather than all of these symbols, because this is what we're going to use when we apply the fundamental theorem to graphical problems. So for example, actually I've got some graphs down here that I'll use to explain that. But to backtrack, this symbol here is our integral. So if we ask you to evaluate an integral function, we're asking you for the change in the original function on that bound, assuming that that integral is bounded. If we ask you to evaluate an unbounded integral, we're just asking you for the original function, with a little bit more specificity, but we'll get to that in a second. And we'll talk about the plus c if you're familiar with that, with the integration constant, if you're familiar with that from perhaps a past calculus class. But the reason why I've introduced these unbounded integrals is because when we get down to the common integration formulas, since those formulas are generalized and they're not being applied over to a specific function or over a specific range, we are going to have that plus c, that integration constant. And so we'll talk about that in this next section. Any questions so far on my introduction to the fundamental theorem of calculus? Okay. So bounded versus unbounded integrals. Our first example here is a bounded integral. I started with probably the simplest function I could ask you guys to integrate. So I'll remind you that when you are asked to evaluate an integral equation, what's really being asked of you is what function, when differentiated, gives f of x being the derivative here. So whatever's in the integral is a derivative. Whatever function, whatever constant is here is the derivative of something. And so what we want to do is we want to find that something. So what function has the derivative of 1? The derivative of 3x would be 3. So the derivative of x is equal to 1. And then this symbolism here is how you represent. So this information here is important. We want to evaluate the change in x on this interval. So this is how you notate that when we're talking about the quote unquote original function, the antiderivative of the function. And so when we further evaluate these, the way that we do this is we plug in top first and subtract the bottom, in the same sense that, in the same sort of format that can be found in the definition for the fundamental theorem of calculus. We're basically doing change in y, f of 2 minus f of 1, or f of x2 minus f of x1. So we're evaluating the change in the original function, which in this case is 2. And so just to backtrack one more time, reiterate this, since this is probably this is going to be the first time that a lot of us are seeing this. This is our derivative. We need to find the function that when you take the derivative, it's equal to what is next to the integral. The dx is important. You've got to keep the dx. If you don't write the dx, you will lose points for conceptual misunderstanding, although I recognize the irony in the sense that I haven't explained to you what that dx is yet, but we will get to that. That's something we'll go into in depth in the future. And then, yep, that's all I really wanted to go over about that. So let's take a look at the graphs here and see what that looks like. So first I've got the graph of f of x. So I'm going to make a note to myself to change this. Well, I guess I'll just do it now. So this is big F. This is the quote unquote original function, the antiderivative function, or not the anti. This is the anti. So this is the graph of the antiderivative of this derivative here. So what corresponds? So going back to this part, this interpretation of the fundamental theorem, the area underneath the derivative of a function on a given interval is equal to the change in the function on a given interval. So regarding the change in the function on a given interval, from 0 to 2, as specified by our bounds over here, we want to know what the change in f of x is. So on 0 to 2, x increases by 2. So that's equal to, so that tracks with our symbolic representation over here, and we'll see how that tracks with the graphical representation of the derivative in a second. But let's unveil this. The change in f of x, this should be big F, is equal to so the symbolic portion tracks, and it's equal to 2. Now let's talk about the area underneath the curve, underneath the derivative curve. So that's what the symbol means. This means the area underneath this derivative on 0 to 2, a to b. That's, if you want to think these symbols in English, think about these symbols in English, that's what this means, is the area underneath this, or take the antiderivative of this derivative. But if we look at the graph over here of f prime of x, this is the graph of 1. And well, I guess my symbolism tracked, but I'll just make a note to make sure it's all cohesive with the definitions that I've given you guys when I send out the recitation note later on. But the area underneath this curve, underneath this straight line in this case, on the interval 0 to 2, we'll evaluate this area just like we do evaluating any rectangle. It's 2 times 1, which is equal to 2. And once again, we get that the area underneath the derivative on 0 to 2 is equal to the change in y. So we've just corroborated this, this interpretation of the fundamental theorem, which is the exact same as saying this in this case. So now let's talk about an unbounded integral and what that looks like. So we won't do examples with unbounded integrals today, but it's still worth it to introduce them, especially since we're going to be talking about these general formulas, and I don't want that plus c to throw you off. But this is something that we will go in depth in the future. For example, we'll do problems where we ask you to evaluate an unbounded integral, and then your answer will have a plus c in it. And then we'll give you some more qualifying information and ask you to determine what the c value is. So this is something that we will have problems on in the future. So you may want to make a note to refer back to this explanation here for when we get to those problems in the future. I will go over the plus c again when we get to problems that include evaluating the plus c, but I won't go over it in such depth as to compare and contrast with graphs. So if we've got the same integral, although it's unbounded in this case, we're going to have an x again, right? The only difference here is that we're going to have a plus c. And what we're going to talk about before we get into the antiderivative formulas and those examples is why the plus c, what it is, what it means, why we care. So if we consider these two functions, h of x equals x plus 6 and g of x equals x minus 100, if we were to take the derivative of both of those, we would get the exact same derivative. And so if we're taking an antiderivative, technically if I asked you to, so if I threw a squiggle in here, and a dx, which I'm not going to do for the sake of time, but if I asked you to evaluate what the antiderivative of h prime of x was, you would say, well, there's definitely an x, but I don't know for certain what the constant is. And that's what that plus c represents, is the fact that it could be 6, could be negative 100, could be some wild, absurd number. It doesn't matter. The point is that since we're only given information about the derivative, we don't know what the constant is. And so graphically, the consequence of this is that it could be a number, it could be infinitely many functions within a family where their qualifying characteristic is that they all have the same derivative. So all of these options here have the same derivative, but all of their plus c's, their constants, their intercepts are different. And so while they have the same derivative, and that's what we're able to get from this unbounded integral, since we don't have the specificity of the bounded integral, we're not able to determine what this plus c is. And so we represent that with the plus c. So to read this little note I've got down here, these are all possibilities for f of x, but without the bounds, we can't find the plus c, and we don't know the unique intercept. And so again, both have the same derivative, regardless of the intercept or constant. So any questions on bounded versus unbounded integrals before we move into the formulas and examples? Okay. So antiderivative formulas. I don't want you guys to scramble to write these formulas down right now. I would just take a screenshot if you would like to be able to swipe back and forth and refer to them for the time being, but don't waste your time scribbling all these down. As you know, I'll send out the recitation note later, and I will, and as we go through these examples, we won't really refer back to these formulas very much. And the reason for that is that except for 2 of these formulas, a lot of these antiderivative quote unquote formulas can be backtracked from what we've already taught you about derivative or differentiation formulas. So for example, I didn't introduce a formula to you guys to be able to explain in like the reverse direction what the antiderivative was, because we all know how to take the derivative of x. So we can kind of take steps backwards in order to figure that out. And the same can be done for the power rule here. So this is the reverse power rule. These are the 2 that, let's see, I've got, just wanted to double check, make sure I didn't have any questions in there. These are the 2 that if I were to say that you had to memorize a couple, these 2 would be them. Not that they're all that difficult, they're actually very straightforward, but we haven't done a lot with Euler's function in terms of differentiation, but typically we do a bit more with Euler's function, E being Euler's function, when we're finding antiderivatives. And then this is just to recognize that the derivative of the natural log of x is 1 over x. So then to evaluate 1 over x dx would be to get a natural log of x for the derivative. So other than that, though, these are all, I guess I shouldn't dot these. So these are the two that maybe we don't have enough understanding of in order to backtrack them and figure them out without referring to formulas, even though they're simple enough that you should be able to memorize them and not actually have to refer to the formula. These two, and then our trig antiderivative formulas, are just the reverse of what we already know about taking derivatives. So for example, we know that the derivative of cosine is negative sine. And so if we were to try and figure out what the antiderivative of sine is, we'd have to throw in that negative there in order to balance that out, because we know that the derivative of cosine is negative sine. And so the antiderivative of positive sine would be negative cosine. And then the same goes for all of the other ones that we know. So obviously there are other trig derivatives that you guys have had to use. So there, when we were doing differentiation, these weren't the only 4. We didn't just want to know what the derivative of sine and cosine and secant, or sine, cosine, tangent, cotangent were. There were others, but it's the same sort of backwards methodology. And I point that out to say that while this list is a good jumping off point, and it is the majority of the formulas that we will use for antiderivatives, if you come across another formula during whether it's on WebAssign or say if it's on a homework assignment, I don't see your WebAssign, I don't look at your WebAssign, and I only grade 2 problems from your homework assignments. So don't count on me to provide you guys with an exhaustive list of these, although this is, like I said, a very good jumping off point, and these are going to be the most commonly used antiderivative formulas. So moving in to our examples. The first one that we're going to do, and I hope that we can recognize that this is going to be a reverse power rule problem. We've got some variables that are raised to 2 powers, and then we've got constants out front that we're going to learn how to deal with today. So I would say that if you're comfortable with the backtracking, if you're comfortable first with taking derivatives and you've got those, I don't want to say memorized, but you've got a handle of those. And if you get a handle today of the backtracking in terms of, so if you don't have to use the formula and you're able to think backwards and figure those out, the big thing to get a handle on today would be how to make these powers line up with your constants, specifically when we're talking about the power rule. And then when we're not talking about the power rule, we still got to make things line up with our constants. And we'll see what that looks like in a second here. So first thing that we're going to do, I'm going to wait to show what the answer to this is. But first thing that we'll address is this first term here, this 4/5 to the t cubed. So this is the derivative, to remind you. This is the derivative of a function. And what we want to find is the antiderivative. And so to do that, we got to think, okay, we know that when we take the derivative by the power rule, we reduce the power by 1, and then we also drop that power down front. So in order to go backwards, we're going to add 1 to that. So we'll do 3 plus 1, which is equal to 4. So then we know that a 4 had to be dropped down. So that means that this 4 here is a part of the derivative. The 1/5, that was there beforehand. I'm sorry, guys, excuse me. All right. So like I was saying, we have to raise it, we have to increase the power by 1, and we know that that power is going to be dropped down front. So it used to be a t to the 4th. And then in order to take the derivative, we subtracted 1 in the power and we dropped that 4. The one part of the constant that's unaccounted for is this 1/5. So that means that our answer to all this, or not our answer, our antiderivative to this first aspect of the derivative is going to be t to the 4th over 5. And once you find this answer, it's relatively easy to double check yourself because it's relatively easy to do the power rule. So it's really just figuring out that constant. Once you get there, you're going to be pretty confident in your answer because you can just take the derivative to double check yourself, which when we drop this 4 and reduce by 1, we get 4/5 t cubed. So now looking at the next part, if we're talking about 3/4 t squared, this first example is easy on purpose. So you can probably, if you understood what I just explained before, you can probably visualize that this t squared, when we took the derivative, originally was t cubed, and that we had to drop a 3 in order to apply the power rule. So it would have been 3t squared. If the original function, or this aspect of the original function, was just t cubed, then the derivative would be 3t squared. Well, we've got this 1/4 to account for. And so, that should have been a 5 for this one. But we've got this 1/4 to account for. And so that is going to be what this aspect of the derivative looks, or of the antiderivative looks like. So finally, we've got 2/5 t. So we know that it had to be t squared originally, and that we had to reduce by 1, giving us t to the first, and drop the 2. And so the only aspect of the constant, or the coefficient, that is not taken care of is that 1/5. So t squared 1/5 is what that aspect of the original function of the antiderivative is. So let's see if all of that tracks. That shouldn't have been 3. That was incorrect there, but my explanations were all still correct. So that's what our antiderivative looks like. And when we're doing these bounded integrals, so the example that I gave before, I used this line to represent the bounds. So you can still do that, but typically when you get into these more complicated functions that have multiple aspects, it's better represented to have these brackets enclosing them, but you wouldn't lose points for using one notation versus the other. So again, what we do now that we've evaluated what this original function, what this antiderivative is, we're going to plug in our top bound and subtract our lower bound in order to find what the change in f of x is. So the area underneath this derivative is equal to the change in the original function. To reiterate that fundamental theorem again, that's why when I was learning in high school, it was hammered into our brain, because that's how you're going to keep that's how you're going to keep this relationship in check, especially when we're talking about graphs. So plugging in these values, I'm not going to go over much about the algebra. We all know how to simplify fractions. Our answer ends up being 2 after all of these simplifications. So I want to make 2 points before I ask if anybody has questions and move on to our next problem. First being that this is the only example in today's recitation where I will go in and plug in these zeros. It gets a little bit redundant. If there isn't a constant, and by say like there was a +2 here, then I would write in those zeros. But other than that, unless you're dealing with trig, so sine of 0, cosine of 0, whatever, we don't care what this is. We don't care about specifically what it looks like when you plug in, because it's just going to shake out to be 0. So unless you've got a constant, or unless you're dealing with trig, if you're subtracting a lower bound or an upper bound of 0, it's perfectly acceptable to just say minus, and then maybe in parentheses to make it clear what you're saying, -0. You'll see what I mean when we get to another example with a lower bound of 0. The other thing that I wanted to mention, first of all, there are a handful of you guys who will make your answers very neat on your exams, and you'll kind of do like a key legend on the side where you'll box in all of your answers. That's great. I really appreciate that. And I know Dr. Zlecki does too. It speeds up the grading process. So when I say that it would be helpful for you guys to simplify your answers, that doesn't mean that I'm taking back what I've said all semester about not wanting you guys to waste time on the exam with oversimplifying your solutions. Say, for example, you're just asked to find a derivative and you spend a bunch of time finding what the simplest solution is. That's still true. I don't want you to waste your time, and I don't want you to open yourself up to the possibility of more mistakes. With that being said, we'll get to an example later on that's got a lot of aspects and a lot of fractions, and it would be nice if you guys could at least consolidate the obvious terms. Again, don't waste too much time. And if you're not comfortable and you think you might make mistakes, that's okay. But it kind of muddies up the grading process. And I don't want to say that you're going to lose points for not doing it, but there's a higher chance of maybe there being a mistake on the grader's end if you've got a lot of different aspects to your answer than if you've got a more streamlined answer and it's easier for us to tell what your answer is. So any questions on the reverse power rule for this first example before we go on to another reverse power rule example? Okay. So now we've got bounds of 1 to 9 and we've got the square root of x. So just like when we're taking derivatives, we're going to do a fractional power manipulation in order to expose what that fractional power is so that we can apply, in this case, the reverse power rule. So that's going to look like the integral from 1 to 9 of x to the 1/2 dx. So if we're going to do the reverse power rule, we've got to add 2 halves. So that means that our original function was some constant times x to the 3 halves. And we know when we take that derivative, here, I'll write this out. So there's going to be some constant out front that I haven't written yet, and we know that the original function was to the 3 halves power. So when we take that antiderivative, or take that derivative, excuse me, we dropped 3 halves. So there's a 3 halves as a part of the derivative. But our derivative doesn't have that constant. So we've got to add something in that's going to cancel out that 3 halves such that it's equal to 1. So what's that going to be? It's going to be the reciprocal. So this would be the formula for the derivative. So what that looks like for the antiderivative, it's going to be 2/3 x to the 3 halves. And now that we've arrived at that answer, it's pretty easy to corroborate that our answer is correct. We drop the 3 halves and we get a constant of 1, which is equal to what we've got here in our integral. And then when we subtract two halves, we get 1/2. And so we know we've got the correct answer. So now we've got to plug in our bounds. And I will go over a little bit of the simplification on this one, just because I think it's always beneficial to go over power manipulations. Students tend to struggle with it. So, excuse me. This 1 here doesn't matter what power it's raised to. It's always going to be 1. 9, however, we've got the upper, so we've got the numerator and the denominator of this fractional power to address. And if you guys recall from past recitations, I always recommend that you address the lower, or that you address the denominator of the fractional power, because it's always easier to go smaller and then get bigger than it is to say cube 9 and then try to find the square root of that. It might not be possible. And so if we first take the square root of 9, we get 2/3 3 cubed, and then 2 times 1. And now we'll cube 3, and we get 27 times 2/3 minus 2/3, which shakes out to be 52/3. So again, don't waste your time scrambling to write down the simplification of these solutions. You will get this note shortly after recitation today, and just focus on the calculus for now. So next example that we've got, sine of theta d theta. I'm going to zoom out a little bit. So this goes, so we don't have to refer back to the formula to figure this out, but we just talked about this. We want to find the antiderivative of sine of x. It's got to be negative cosine of x. And that's because we know that the derivative of cosine of x is equal to negative sine of x. So we've got to add in that negative to make our constant line up, in the same sense that we had to add in the 2/3 to make the 3 halves cancel, right? When we drop this 3 halves here. The name of the game after you figured out what the antiderivative is just making sure that your constant or your coefficient is equal to, or it will be equal to, what's given in the derivative. So if we don't have negative sine of x, then it doesn't fit our typical mold, our typical formula for the derivative of cosine of x. We know that there's going to be a cosine of x. We've just got to figure out what coefficient is going to make everything line up for us. And in this case, that coefficient is going to be -1. So -1 cosine of theta over the same bounds is going to look like this. I know I harp on you guys about parentheses. It's especially important when you're doing these problems that you use parentheses every place that you plug in, especially if you're someone who's error prone. And this is an obvious example of why. I can't tell you how many students will lose points because they subtract when, or whatever it is, because their signs don't match up because they don't use parentheses. And so there are two situations where you should be using parentheses. You should be using parentheses for every place that you plug in for an x, a theta, a t, whatever. And then you should be using parentheses to group together the f of x with the lower bound. So like I did here, you should always use parentheses around the second one in order to represent that this negative sign is being distributed to all elements within the parentheses. And then again, in this case, even though there's one element in our derivative, we still have to have this negative parentheses negative because we have 2 negative signs to deal with. And that's going to change our answer if we forget one or the other. So now we've got to evaluate what these actually are, negative cosine of pi and negative cosine of pi over 6. So we'll refer to our unit circle. If you're still not comfortable with the unit circle, definitely seek out a Khan Academy video. This isn't going away. I've been saying this all semester. We will continue to use the unit circle up until the very last thing that we teach you before the final exam. And so looking at negative cosine of pi, pi is all the way over here. Cosine represents x values. And so the width of the x-axis here, since it's a unit circle, is 1 or -1 specifically, because we're talking about pi, which in terms of coordinates is in the negative x-axis. So -1 is going to be our first answer. -1, yet another example of why you should always plug in with parentheses, because if you were to write that, if you were to just write down -1, you might forget this negative sign here, and that would change your answer. And then our two negatives cancel out such that we have a positive. And from the relationship between special right triangles and the unit circle, I know that the width of pi over 6 here is going to be square root 3 over 2. So our final answer is 1 plus square root 3 over 2. We've got about 4 more problems to go over. Does anyone have any questions on anything I've introduced so far? Fantastic. All right, so next example. Let's talk about what these examples so far have entailed. So these first two, 21 and 23, both reverse power rule examples. And that should make sense. This one here, I think this is the only trig one that we do. Yep, it's the only trig example that we do for today. But for these last few examples, the main thing that we're going to do is, well, the integration technique that we're going to use is the reverse power rule. But what makes these unique is that we've got to do some algebra beforehand, and that's something that has been standard throughout the course. You might know what formula to apply, but you also are going to have to get it into a quote-unquote workable form first in order to apply the power rule, because we don't have a reverse product rule per se. If you were taking the derivative of this here, you would use the product rule, or maybe you would distribute first and then use the power rule, whatever you chose to do. But we haven't taught you any sort of a reverse product rule. And so to get it in a workable form, we're going to have to FOIL these two out. And then we've got another example that requires foiling down here. And then these two examples are going to require us to distribute the denominator. So we'll look at that more closely in a second. Circling back to just foiling these two out, we're just going to do what we always do. U squared minus u minus 6 is equal to this here. And now that we're taking the antiderivative, so this is the first example that we've done of the reverse power rule that doesn't have a constant for us to work with, I believe. So if we know that this is, if we know that the original function must have a u cubed in it, and when we take that derivative, we're going to drop the 3. So -1 would be 2. Got a 3 here. What constant can we add in that's going to cancel out this 3 such that we have a constant of 1? The reciprocal of 3 over 1 is 1/3. So we're going to add in a 3 in the denominator. So that means that we've got u cubed. Oh, that's new. U cubed over 3. And once you figure this out, it makes it pretty easy going forward. I don't think there's too much explanation merited for this versus the other ones. But whenever you see something that's got a power, but it has no constant, when you raise it, you've got to put that same power in the denominator. So if it's cubed, you got to have a 3. If it's to the first, then that means that our antiderivative is going to be squared. So in the denominator, we've got to have a 2. And then this is the same as the first example that we did, where the derivative of x is 1. So we get 6u on the interval 0 to 1. Let me erase this really quickly. So now we're going to plug in our values. And from here, we've done all the calculus. This is the brunt of the work, and it's just simplification. Excuse me. This is what I meant by it's perfectly acceptable. So it gets pretty redundant. If you were to have to rewrite all 3 of these terms with a 0, when you know that it's all going to shake out to be equal to 0 anyways, that's a waste of time. And I don't expect you, and nor does Dr. Zalecki expect you to waste your time like that. So it's perfectly acceptable to just write -0 to encompass this entire lower bound term, which shakes out to be equal to, well, the lower bound term doesn't. The whole antiderivative shakes out to be equal to -37/6. So like I said, this one is an example where you have to FOIL. And so is this one, or excuse me, this one. And now we're going to talk about distributing the denominator, which just like foiling is just one extra step that you've got to do. We might have to do a fractional power manipulation. Looks like since we've got a square root here, we might. So I don't want to say that every time that you've got a power that's got something in the denominator that it's sufficient just to distribute that denominator. There might be other steps that you've got to do too, but we'll see what that looks like. So first thing that we're going to do is we're going to break them up. And like I said, we've got a fractional power manipulation. So, and by that I mean I have changed the square root of x and represented it as x to the 1/2 power. So now let's look a little more closely, because like I said, I like to go over these fractional power operations because students tend to have a tougher time with them. So we know that this is going to be, when we pop this up in the numerator, because when we do the power rule, we do things in the numerator because nobody thinks that's how we taught you to do the power rule. So we know this is going to be -1/2. So basically, when we are dividing by another fractional power, we just subtract that power from the power on top, which should make sense because we're comfortable with the fact that 2 over the square root of x is actually equal to 2x to the -1/2. So in this case, division shakes out to be subtraction of the powers. So what that looks like for this one, actually, I'll just unveil the answer, is 2x to the -1/2 plus x to the 3/2 dx. And so at this point, now we need to take our antiderivative. So we'll talk about this one since we've got the time. We've got 2x to the 1/2, which means that originally our function was x to the 1/2. So if we know that we had to drop that 1/2, that means we got to add in another constant such that once we multiply that constant out front by 1/2, that's equal to 2. So what times 1/2 is equal to 2? That's 4. So 4 to the 1/2 is going to be the antiderivative of this aspect of the function. So when we drop that 1/2, we get 2x to the -1/2. Same thing for x to the 3/2, except now we've got 5/2. So in order to take this derivative, or once we take this derivative, have a constant of 1, we've got to have 2/5 out front. 2/5 x to the 5/2 is going to be the original function that gives us x to the 3/2 as our derivative. So that looks like this from 1 to 4. So now we're going to plug in first our upper bound and then subtracting with parentheses our lower bound. All of these shake out to be 1 because it doesn't matter what power you raise 1 to be, it will always be 1. And again, you're going to address the lower or the denominator of the fractional power first. So we're going to take the square root of 4 before we put 4 to the 5th power. It's a lot easier to manage smaller numbers and then get larger than the other way around. And so, like I said, I'm not going to spend too much time talking about how to condense these fractions, but our answer ends up being 82/5. So now we'll do another foiling example. How much time we've got? Oh yeah, 10 minutes. So on 0 to 1, 1 plus r cubed dr, what original function on 0 to 1 will give us this derivative? So first thing that we're going to do in order to determine that is we're going to FOIL out what's going to take 2 steps of foiling because it's cubed. So we've got 1 plus r times, and then this is equal to 1 plus r squared. And then we FOIL that out once more. And then I'm sure you guys are writing this down, so I'll give you one more second. But then we'll consolidate those terms such that we get r cubed plus 3r squared plus 3r plus 1. And this was the example that I was referring to earlier when I said that in terms of grading, it would be nice if you guys didn't leave us a bunch of fractional answers, because when you end up evaluating this, you're not just going to have you're not going to just have 4 aspects of your answer, you're going to have 8 because it's the upper bound minus the lower bound. Specifically with this problem, that's not an issue because the lower bound is 0. So when we plug in, it's going to end up being 0 for the entirety of the lower bound term. But say that this was from 2 to 1, that'd be a lot of fractions for the grader to have to consolidate, and it's a bit of a gray area on whether or not you should or shouldn't do that. But point is if you've got easy fractions and you're comfortable with putting them together and simplifying your answer, then in terms of getting your exams back quicker, that would be recommended to do. So now we've taken our antiderivative. Maybe I shouldn't have unveiled it so quickly, but these are all these are all pretty simple. So this is r cubed, which means that originally it was r to the fourth. So how do we get a constant of 1? We put 1/4, or we give the original function, that aspect of the original function, a constant of 1/4. So looking at the second aspect, we've got 3r squared. This one's pretty straightforward. R cubed, when you take the derivative of that, you drop the 3, reduced by 1. Now we've got 3r, which originally would have been r squared. So we don't really worry about the 3 too much because we know that's not going to help us to cancel anything out. What we do is we add in a factor of 1/2, or we multiply by a factor of 1/2. So we add in a 2 to the denominator. And then finally, what's the derivative or the antiderivative of 1? When we're taking the antiderivative with respect to r, that is r. So on the interval 0 to 1, when we plug these in, this is what we get, and our final answer is 15/4. Finally, we've got one example left to do, and this is going to be another example where we have to distribute the denominator. So we don't have to do any fractional power manipulations per se because we don't have any square roots or anything like that, so this one will be a little bit more straightforward. So like I said, when you've got something, so when you've got the same variable and you are dividing one on top and one on bottom, and they both have things, they've both got powers. So it wouldn't matter if it was just v in the numerator. It would be v to the first divided by v to the fourth, which is equal to v to the first minus the fourth, which would be v to the negative third. So in this case, our answer for this first aspect would be v to the first, because we're doing 5 minus 4. And then to the second aspect, it would be 3v squared, 6 minus 4. So now that we have determined that, we've gotten our answer, or we've gotten our given information into a workable form, now we can take the antiderivative, which, so for this first term here, it must have been squared originally, so we get v squared over 2. For this term, it must have been cubed originally, so, and we don't have to worry about the constant because when you drop the 3 for v cubed, that tracks with what we've got for our derivative here. So this is our antiderivative, and plugging in those values on 1 to 2, we get 17/2 as our final answer. All right, so we've got, oh, we finished up early today. We used all the time during the first recitation. I will stop the screen